Hi, welcome to an introduction of the network analysis in the context of quantitative encephalography. We will address some concepts as connectivity, graph, and complexity measures to understand the brain network correlates extracted from EEG signals. All concepts addressed here can be extrapolated to other data as local field potentials or data from brain electromagnetic sources. So, if you have any neural data, you can infer the associated underlying brain networks. Considering that the EEG have been acquired and pre-processed in this hands-on presentation, we evaluated a connectivity measure between the EEG channels. So here we have 52 channels, and the connectivity measure is how much those channels are communicating to each other, the interactions. So, after the connectivity measure calculations, we obtain a 52 square matrix. In here, we calculated during 10 epochs. Let me show you a connectivity submatrix of order 8. The main diagonal represents the channel self-interaction, and it was discarded. The first line exhibits how much the first channel interacts with the other 7 in this submatrix. Those connectivity values can be derived from a functional connectivity measure when it's based on statistical dependence of the channels, or from an effective connectivity measure regarding causal relations between channels. This example here takes in account an effective connectivity measure, and you see how much a channel is causing another one in the sense of information transfer. So, the start point of the neural network calculations is the connectivity matrix. After that, we have to define a cutoff point, a threshold, to transform this real value matrix into a graph representation, a binary representation called the adjacency matrix. For instance, if we choose the standard value 0.5 as a cutoff point, you see here the respective adjacency matrix. Lower than 0.5 is 0, and greater or equal 0.5 is 1. Or we can choose another threshold, for instance, the median of the connectivity values, and another adjacency matrix for your choice. Let me show you now a dynamic graph representation of the neural networks during the 10 processed epochs. You are observing a dynamic neural network evaluated in the delta band after a neuromodulation procedure. On the right, you see a color map representation of the connectivity matrix, values from 0 to 1, real values. On the left, you see a graph representation where the channels are the nodes and the connections are defined by the 1 values in the adjacency matrix. During this session, we notice the graph representation changes for each epoch. In the last one, we see the EEG channels talking to each other through a connectivity measure. This conversation is dynamical and can be analyzed by its three-dimensional representation or by its two-dimensional representation, different levels of information. So, the graph nodes are the channels, and the graph edges are defined by a connectivity measure. Let's see now two concepts of the graph theory. The first one is the clustering coefficient, which is the ratio between the number of connected neighbors and the number of all possible connections. For instance, you see here this channel O2. You count the actual connections of O2 and divide by the all possible connections with the neighbors. This will provide its clustering coefficient. In more dense regions, you expect to find greater values of the clustering coefficient. The second concept is the shortest path length between two nodes. It's about the minimum number of steps to connect the nodes. For instance, between F1 and F3, you have one step. But between F3 and FC3, you're gonna have more steps. Could be 3, 4, 10. So each node has its cluster coefficient. It's about interconnections. And each pair of nodes has its shortest path length regarding extra connections. If we average those measures over the nodes, you get global parameters of the graph, complexity measures for the neural network. Let's review some concepts. We start with a connectivity matrix. Here, just a submatrix. Then we define a threshold and obtain an adjacency matrix, which will generate a graph like those ones on the right. It's important to notice that for each epoch of the session, the neural network changes, and the merging patterns and their shifts are fundamental to analyze the neural correlates, for instance, the ones associated with neuromodulation. So, we have a lot of information from a specific narrowband, here, delta band, of how much the channels are interacting through a connectivity measure. For each graph, we calculate the average clustering coefficient and the shortest path length, global parameters of the graph complexity. For each graph obtained from the 10 epochs, we normalized the clustering coefficient, and we also normalized the shortest path length using random graphs with the same parameters. The ratio between the cluster coefficient C and the shortest path length L through normalized values defines a new complexity measure called small world parameter, S. When S is greater than 1, that is, when C is greater than L, the neural network exhibits a small world behavior. Formally speaking, small world behavior happens when L grows proportionally to the logarithm of the number of nodes. But we can understand small world as an efficiency measure of the neural network. Small world behavior arises, for instance, in the presence of hubs on the graph regarding to high C values. Those hubs are linked by long connections and no isolated nodes, providing low L values in the neural network. Here, C and L for the 10 epochs, and here the respective S values, which when greater than 1 determines the small world behavior. You see the oscillations here and here, and in the S values, you can see the pattern shift during the session, from which we can infer the subject's neurophysiological states. As an application example, let's assess the TDCS neuromodulation efficacy, analyzing anodic, cathodic, and sham conditions within groups of severe and moderate pathologies. For each condition, each group, the EEG signals are decomposed to a specific narrowband, and then we evaluate the sets of parameters C, L, and S to apply inter and intragroups hypothesis tests. On the left, you see the intergroup hypothesis test for the small world parameter, and on the right, you see the respective box plots. Before TDCS, for most of the bands, there is no significant differences, but after TDCS, for the alpha band, you see significant differences between anodic and cathodic conditions, moderate and severe pathologist groups, indicating that the small world parameter is sensible to the application of TDCS. And here you see the intergroup hypothesis test for different conditions and levels of pathology. You see here specific bands, a significant change of the small world parameter, but not on the sham groups here and here, indicating that the small world parameter is sensible to active TDCS. So the S values distributions after the neurostimulation inter and intragroups exhibit significant differences, considering 1% significant level. We conclude that the small world parameter is sensible to the neurostimulation therapy. The small world parameter is a biomarker to assess the neural networks inferred from the quantitative EEG analysis. It is used to support brain pathology diagnosis and neuromodulation therapy follow-up. Here, I give you some reference to go deeper in this introduction, and I thank you for your attention.